Hello and welcome. In this video, I'm going to be talking a little bit about how to reason about performance and computational complexity in APL. In particular, this is sort of a response to some comments to a recent code report video. In an older code report video, Connor Hoekstra has gone through a single programming problem and solved it in many different programming languages, comparing the different sort of approaches or the way that, different ways that they look. Recently he's released another video with 4 more programming languages and an extra APL solution. So in both videos he's gone into a bit more detail about the APL solutions that he has here. But then a couple of people have commented asking about how do you reason about the performance of APL code. In particular, Corv says it might seem elegant and all, but trying to reason about unknown algorithms seems tough. And I think I would have agreed, but something that I've been told by different people at different times, and something I've experienced quite a lot when using APL, is that if you have a solution which is basically, a single line or a couple of lines composed primarily as much as possible of the primitives and using the primitives well, then reasoning about the computational complexity in the worst case scenario is basically just combining the complexities of the individual primitives. So once you know those, you know the complexity of all your solutions, and being able to tweak them is fairly straightforward. So I have here 3 different expressions of this, the APL solutions to this problem. I won't go into the details. You can watch Connor's videos, which are linked in the description below. But basically it's given some expression which contains parentheses, what is the deepest depth of nesting, right, parentheses. So from the outside is 0, then you go in 1, that's level 1. If you go in a second time, that's level 2, but you come out again, that's level 1. Go in again, that's level 2, and then the deepest here is level 3. So I'm going to talk about the computational complexities in very broad terms of both of these expressions before showing you how to compare the actual runtimes of APL expressions. So here's the first one from Connor's first video, which is basically using a compress to isolate the parentheses, doing some comparison, a bit of arithmetic, and then we'll see this pattern in all of the solutions, a plus scan followed by a max reduce. So the only difference really in each of these is how to get to the vector of 1s, 0s, and -1s that kind of tell you if you're coming into a new depth or out of some parenthesis depth. And here I've written all of the functions which are applied, about in the order in which they are applied, along with a sort of worst case estimate of the computational complexity in big O notation. So let's go through these one by one. So membership here is a sort of comparison function, right? You're going to return an array the same shape as alpha, but with a 1 indicating that an item in omega has been found, right, is in that position. So in the worst case, you're actually comparing every single element of alpha to every element of omega, and that would be kind of quadratic, order n times m, where n is the length of alpha, m is the length of omega. But here, in theory, because we have, a constant right argument here in the, that's just 2 parentheses, then we know we're always going to have a result that's twice the length of our expression. So really, this could be reduced to a linear time algorithm for our particular use case. Then equality comparison on 2 arrays is basically linear in the length of either of them, if they're the same shape, or even if one of them's longer and one of them's a singleton. Then we have replicate, or in this case we have a Boolean left argument. Boolean alpha means it's compress, and that's also linear, just traversing the longest array there, or both arrays are the same size. Then we have not, which is just with a binary, with a Boolean vector, turn the 1s to 0s, turn the 0s to 1s, and that's just traversing the length of that array. Subtraction, again, basically just linear. Plus scan, unfortunately, scan in Dialog APL is implemented in the general case as n squared. So you can demonstrate this by basically initializing some counter, and then in my defin here, if I use jot gets, then this basically is a global assignment indicator. So increment the global variable I every time this is run. Otherwise, I'm just going to be doing plus, so we get the same result. So plus scan, this is a general scan of the first 5 integers. You can see we actually hit the function 10 times, which is not optimal for a commutative function. You can actually get this to be linear if you optimize. So I can show you just a bit more clearly. We get about 4 times as many hits if we double the input. If I double the input again, then 4 times as many hits again approximately shows you that that's quadratic with the input. Plus scan though, if you literally use the glyph plus and have this, then that token is optimized within the interpreter and I believe should be linear. So that helps. And now you can see what is in principle a quadratic algorithm through our particular use case could be thought of or could be optimized up to linear in terms of the length of our input. Okay, so the second one here is kind of a bit more elegant. I guess it's shorter. You might think of it as a bit more idiomatically APL-ish, and it was found in an old paper by Ken Iverson where we're utilizing an outer product here. So really, once again, this is n times m in the worst case, but once again, since we've only got 2 elements and a fixed input, then in theory it's linear in terms of the length of omega. Then we've got another subtraction, then another scan, which has the exact same optimization I just showed, or just talked about, and then the max reduce again. So even though it's different in terms of the details, the reasoning away some of the computational complexity is basically exactly the same. Now, of course, what you want to know is how do they actually compare. So in Dialog, you can use the runtime user command, which is actually just a thin wrapper for defin's cmpx, but I like using runtime, so that's what I'm going to use. And runtime compare, and then we can look at our 3 expressions, our 3 different solutions, all with the same expression. And I'll show you what pdep3 looks like after we see the comparison. Right, so if we look at the 3 of these, then we can talk a little bit more about what the differences are. It looks like the Iverson one is quicker in this case, but I will give you the caveat that we're looking at 19 characters in our expression here. I think in particular it's just the fact that we're doing less parsing. There are fewer symbols, fewer operations overall. That probably accounts for most of that. And you can see with the third one, which is basically identical to the outer product, but instead of doing an outer product, which allocates flat arrays, we're enclosing our argument, creating a nested array, and then using each. So let's say that we had another expression, which is 1,000,000 elements long. We compare all of these. That's going to be a bit more interesting. So Iverson's loses out quite significantly at this point. And I'm thinking that this might be taken into account that once you do this outer product, you still have length omega elements overall, and it's possible that doing the compression here and then the comparison, once you do this compression, anything that's not, you have an array that's only the length of the number of parentheses. That might be the reason. So you end up with a smaller array to do comparisons, and you end up having to do fewer comparisons overall. That might be the case. I'm not exactly sure. The point I'm trying to get at really is that APL is this kind of high-level, low-level language where a lot of solving problems in APL is about having direct expression of your solution. So using the primitives, and it's really easy to refactor and try out different approaches. So you can see here that even though all three of these solutions are essentially expressing the same algorithm, the same basic recipe, right, of generate a vector of ones, zeros, and minus ones, where a 1 indicates going into deeper into the nesting and -1 indicates coming out of the nesting, then do a plus scan and a max reduce. So in that sense they're all the same, but you get to play with the implementation details by trying out different primitives and different ways of approaching that. In general though, a lot of really common APL constructs, things like scans on booleans, have extra optimizations inside that allow them to shortcut, and finish early and things like this. And it's these types of optimizations that make the real performance much more difficult to predict and reason about than the overall performance. But what I hope I've shown here is that you get a pretty straightforward way of reasoning about the computational complexity of any individual solution, because it's made up of, a few well-defined functions which have well-known computational complexity in the general worst-case scenario. That's it for now. Hopefully I haven't said too many incorrect things. Please, people more knowledgeable than me, feel free to say so in the comments. And I'll catch you on the next one.